Hi, this is Fahad Sarfaraz and I will be presenting my joint work with Elahe Arani and Bahram Zinus on synergy between synaptic consolidation and experience replay for general continual learning. Unlike humans, artificial neural networks exhibit catastrophic forgetting when required to learn tasks in a sequence from a continuous stream. Effective continual learning requires a delicate balance between the stability and plasticity of the model so that it has the flexibility to adapt to the new task while retaining and consolidating knowledge from previous tasks. In the brain, this delicate balance is maintained by a rich set of neurophysiological mechanisms and facilitated by multiple memory systems. In particular, our work focuses on two aspects of the learning machinery of the brain. Synaptic consolidation enables the retention of information over longer periods by decreasing the rates of plasticity in a proportion of strengthened synapses, while the complementary learning systems theory posits that intelligent agents must possess two complementary learning systems. The instance-based hippocampal system rapidly encodes novel information, which is gradually consolidated into the structured knowledge representation of the parametric neocortical system through the replay of neural activity patterns. The synergy between these mechanisms plays a crucial role in enabling efficient lifelong learning in the brain. Therefore, we hypothesize that an efficient method of employing a dual memory replay mechanism and incorporating synaptic consolidation for mediating the plasticity of weights can enable effective continual learning in deep neural networks. To this end, we propose a novel method which creates synergy between experience replay and synaptic consolidation in a dual memory architecture. To replay samples from the previous task, we utilize a small episodic memory buffer as an instance-based memory system which can be thought of as a very primitive hippocampus, and employ a supervised loss on the interleaved samples. We maintain an additional semantic memory which progressively accumulates and consolidates knowledge across the task encoded in the subsequent learned weights of the working model throughout the training trajectory by taking an exponential moving average of its weights. The semantic memory loosely mimics the neocortex as it constitutes a parametric memory system that builds structural representations for generalization that interacts with the instance-level episodic memory to efficiently accumulate and consolidate knowledge. Semantic replay enforces the consistency loss between the predictions of the working model and the semantic memory on the buffer samples. Additionally, we track the importance of each synapse by maintaining a running estimate of Fisher information metrics evaluated periodically on the semantic memory using the buffer samples. The important parameters of the working model are then anchored to the semantic memory using the synaptic consolidation loss. To make the algorithm suitable for general incremental learning and enable effective consolidation of information across the task, the running estimate of the Fisher information metrics is stochastically updated throughout the training trajectory instead of using the task boundaries. The Fisher information matrix is evaluated on the samples in the memory buffer as they approximate the joint distribution of all the seen tasks, and the semantic memory is utilized to evaluate the Fisher information matrix instead of the working model, as it effectively consolidates information across the task and provides a better estimate of the optimal parameters. Subsequently, the working model weights are anchored to the important parameters of the semantic memory. Finally, to maintain the functional integrity of convolutional filters, we adjust the Fisher information matrix such that the importance of each filter in the convolutional layer is given by the mean importance value of its parameters. This prevents a drift in the functionality of the filter unit, which might be important for the previous tasks. For our empirical evaluation, we consider three continual learning scenarios. Domain incremental learning refers to the continual learning scenario where the classes remain the same in subsequent tasks but the input distribution changes. Whereas class incremental learning presents a more challenging scenario where new classes are added with each subsequent task and the agent must learn to distinguish not only among the classes within the current task but also across previous tasks. The focus of our study, however, is on general incremental learning setting as it better simulates the challenges in the real world. Where the task boundaries are blurry, tasks are not disjoint, and the classes can reappear and have different distributions. Therefore, we do not utilize the task information for training or inference, and we don't make any assumption about the distribution of the data. The empirical results on different control learning scenarios show the effectiveness and versatility of synergy. We observe performance improvement for the majority of considered settings, particularly for the GCIL long-tail setting where the agent has to tackle with the challenges of class imbalance and sample efficiency. In addition to avoiding catastrophic forgetting, synergy provides considerable performance improvement over previous methods. To gain further insights into the effect of the different components of synergy, we conduct a series of Fibration experiments. We systematically remove the components and show their effect on the performance of the model. The drop in performance from removing the Fisher adjustment step shows that accounting for the functional integrity of the convolutional filter is important and suggests that more specialized algorithms for calculating the parameter importance at the filter level instead of post-processing may further improve regularization. Furthermore, evaluating the Fisher information matrix using the semantic memory on the buffer samples instead of the working model on the current task training data provides a better estimate of the importance of parameters for all encountered tasks. The performance improvement of mean ER over experience replay shows the effectiveness of replay in a dual memory architecture. Importantly, merely plugging the regularization in mean ER not only adds a reliance on task boundaries, but is also detrimental to learning. Online EWC anchors the weights of the model to their state at the task boundary, which might over-constrain the model update and hampers knowledge consolidation. Furthermore, the importance estimates are biased towards the current task. Our proposed modifications, in addition to making the model suitable for general continual learning, enables knowledge consolidation by maintaining an updated estimate of parameter importance across the encountered tasks and anchoring the weights to the consolidated weights in the semantic memory. A closer look at the characteristics of the learned model shows that the final parameters of synergy are considerably closer to the earlier tasks compared to the baselines. This suggests that our method effectively employs synaptic consolidation to reduce forgetting by keeping the parameters closer to the optimal parameters of the previous task. Furthermore, it improves the reliability of the model and mitigates the biasness towards recent tasks. As the stability-plasticity dilemma lies at the core of continual learning, we proposed a new metric to formally evaluate and compare the trade-off between plasticity and stability of the model. Given a task performance matrix, at task T, we consider stability as the average performance of all the previous T-1 tasks after learning task T, whereas plasticity is measured by the average performance of the task when they are first learned, corresponding to the mean of the diagonal of the matrix. We then provide a standardized way of measuring this trade-off. Comparing the performance of the different models, we can see that synergy maintains a better trade-off compared to the baselines. While CoLLAs provides higher stability, this can be attributed largely to the lower frequency of update for the stable model, but it comes at the cost of plasticity. Synergy, on the other hand, not only provides comparable plasticity to DER, but also considerably higher stability. To summarize, to the best of our knowledge, our study is the first to employ dual memory experience replay in conjunction with synaptic consolidation that is suitable for general continual learning, whereby the model does not utilize task boundaries or task labels during training or inference. The intended takeaway message from our study is that employing multiple complementary mechanisms similar to the brain can be effective in enabling continual learning in artificial neural networks. Our study highlights the benefits of incorporating both experience replay and regularization in dual memory architecture and emphasizes the importance of design choices that can enable effective knowledge consolidation. We hope that our work will inspire further research into this promising direction. Thank you.